Chapter 5 deals with stereochemistry. It's a topic that we're going to see throughout the rest of the year of organic chemistry. So there's some terms that we need to understand, and luckily we kind of have an intuition or a natural feel for things like symmetry. So we've seen constitutional, that's a different connectivity, isomers before, and geometric, which are cis-trans isomers. In this chapter, we're going to look at specifically at stereoisomers, and these are molecules that have the same bonding sequence, but they differ in orientation in space. Now, stereoisomers can often have drastically different physical, chemical, and biological properties. So, for example, if we look down here below, here is the molecule that gives rise to the spearmint odor. Now, its mirror image, so if you were to put a mirror right here and draw the mirror image over on this side, you would get this, caraway seed oil. Now, we all know spearmint smells like spearmint, right? We've all had that gum before, or candy. And caraway seeds, they smell, to me, they smell a little bit more cedary, like a little bit more woodsy. But it definitely doesn't smell like spearmint oil. But notice the connection of the atoms is all the same. It's just that how the atoms are oriented in space are different. So these are different molecules, and we'll talk about that, how to determine that in just a minute. So we can consume both of those. That's not a big problem. But we have another molecule here called thalidomide, right? This is TH. Thalidomide, right here, and R thalidomide. So an S and an R version. And we'll talk about what an S and R mean. These are mirror images of each other also. They're not set up so that you can clearly see that. But one of them is given as a sedative, and it's an anti-nausea kind of medication that was given to pregnant women in the 70s. And the other version of this, which is the mirror image version, is a teratogen, which causes mutations in the development of the fetus in the uterus. So children were born that were exposed to this that had malformed limbs. So thalidomide is not something that that we can just take by itself. We have to separate out these two and take the thing that's bad out so that the thing that we want is left and that we can use it. Right? It's safe to use. Now, chirality. Chirality is sometimes called handedness. Now, this is something I would usually ask in a classroom setting. So we have a natural feeling for this. So if you take your right hand, you put it out, and your left hand, they're mirror images of each other, right? I hope they are, at least. So if we have a mirror right down here, we have a left and a right hand. Now, to test whether or not your left and your right hand are identical, and we already know the answer to this, what we do is we put them on top of each other, and we check to see if they are superimposable. Right? So if they are not superimposable, then they are known as enantiomers. So there's going to be some terminology that we have to know in this chapter. So enantiomers are simply non-superimposable mirror images. Right? So that's important. Non-superimposable mirror images. Now, as it turns out, a molecule can only have one mirror image, right? So it only has one enantiomer. You have a left hand, and the mirror image is your right hand, but there's no second right hand. It's just they exist in pairs. So chiral objects cannot be superimposable on their mirror images. And achiral objects are superimposable on their mirror images. And what we're going to have to do is we're going to have to try to figure out how to deal with this situation when we talk about molecules. Now, there are two ways to determine if a molecule is chiral. The ultimate test is to test to see if the mirror images are superimposable. So let's test and see this. So let's look here. Here we have a molecule, and I've just numbered these things 1, 2, and 3. So we're going to label this guy down here green. Let's make it green, and that's our number 2. Right? And then these guys here, I'll just highlight in as being just red. Those are our number 3s. Okay. Now what we're going to do is we're going to construct a mirror right here. And we're going to draw the mirror image of this. Okay. So let's take a look. So number 3, these red guys, those should be facing in towards each other, right? This is kind of like your thumbs. They're facing in towards each other. Now let's take some numbers. Let's put them in. So that's your number 1 up here. And these we said were 3. So that's number 3 here. That's number 3 right there. And then the green atom is facing back right now. So that green atom here is your number 2. And so you got your number 2 right there. All right. Now to test whether or not these are the same, we have to do a rotation. So what we're going to do is we're going to grab a hold of this top and we're going to spin it around like this. All right. So just like you're twisting the top of this molecule. So what we're going to do is we're going to do a rotation here. So we're going to twist. Okay. Now number 1's not going to move. That stays up at the very top. What we're going to do is I'd like to see if this number 2, I want to kind of put it around here, and I want to get that number 2 to be at this position. So if I get my number 2 at that position, then this number 3 that's here is going to swing around and going to be pointing back. So that's your 3 here, and then they're the same atoms. So they're both number 3. And then you can see, well, looky there, we have 2 molecules. This mirror image is the same as that molecule. So therefore, this molecule is achiral. Right, now let's take a look at some models here. So here's the depiction of the models that we were just looking at. So we have our green coming back, our white up here, and our red 3s right here. Here is the mirror image, right? And now to test if they're the same, we need to rotate this guy around. So we're going to rotate it around, give it a slow spin here, right? As we do that, we're lining them up, and we can see that they're the same. Okay. Now the other thing to point out as we go around and do that is the relative position of these atoms. So this atom that's right here, as we rotate around, right, it's out at us right now, but as we rotate this around, it's moving to the back. It's moving to the back right now, and it's going to be pointing back. It's this guy in the back right here. Okay. So that's going to be important when we look at the next little example here. Now let's look at this next example here. So we have 1, 2, 3, 4. Notice that we just simply have 4 different atoms. It doesn't matter what they are, but they need to be different though. And we're just going to label them 1, 2, 3, 4. And then let's color code them also. So let's make this guy here green, and then we'll do a red in the background here, and then we'll make this guy here blue. And we'll leave the atom up at the top is just white. All right, so now the mirror image. All right, now this dash right here is going to be the dash on this side. So that's your number 4 here. And then this wedge guy is going to be pointing out here. So it's going to be pointing the same relative position, pointing out on that side. And that's going to be a number 3 for us here. And then what do we have? We have this green. So we're going to come back here and let's do our green. It's pointing that way. That's like your pinky, right? If you were looking at your hands. And then that's going to be your number 2 here. And then up at the top, easy, that's your number 1. So the first thing is to draw the mirror image. So these are mirror images of each other. Now what we're going to do is we're going to do another one of these rotations. And what I want to do is I want to try to get 1 and 2 to line up. So I'm going to rotate this around, kind of like this. Of course, number 1 is going to stay in the same position. That's not going to move. And then number 2, I'm going to move to this position. So this is going to be my number 2. Right there. Now, as I rotate this around, right, so kind of what's happening here, remember, 2 is coming around this direction, all the way around. That 3 is going to come around here, and the 4 is going to follow it, right? So as that 3 comes around, it's actually going to move into this back position. So my number 3 is going to be right back here. And so there's my number 3, and then that puts 4 here. And this is one of those chapters where models really help. So you can use some free tools that are out there, or you can use your model kit. And there's your number 4. And then we examine here. Remember, this is an original molecule. This is mirror image. So we're testing, are they the same? So when we rotate these around, we can see that 1 matches up, right? 1 matches up, and 1 here. That carbon matches up right there, and then number 2 matches up. But number 3 and number 4 are not matching up anymore. So that makes this molecule a chiral molecule, right? It's chiral. Now we can look at some images of that. So now again, what we're going to do is we're going to take this molecule and we're going to rotate it around. So give it a little twist. And remember, we want this green to be aligned up. That's the alignment that we want. So I'm going to rotate that around. Right, and as I do that, notice my number 3 that's right here. It's pointing out right now. It's on a wedge. Let's see where it's going to go. Okay, so that is on a wedge. Right now it's in plane right now. And then we're going to rotate it around, and now it's going to be on a dash. Right, and then our red atom that was on a dash will be on a wedge. Right, so now when we look at this molecule does not match up, right? 1 and 2 match up, right? These guys here, but 3 and 4 do not match up. So even though these molecules have the same connections to atom, their orientation in space is different. And again, that makes these molecules chiral. So note on that last example, we had a chiral molecule, and that molecule had 4 different groups on one atom. So this is something for us to kind of watch out for. Now there's other tests that we can use too. There's a quick test. So that quick test is to look for a mirror plane of symmetry, sometimes called a mirror plane. It's a plane that divides an object in 2 equal halves that are mirror images. So if an object has a mirror plane of symmetry, the object will not be chiral. It will be achiral. So here's an example. If we look at this molecule, there's 6 carbons, right, all connected together with a chloro group that's facing out towards me, and then a chloro group that's away from me. Well, right down the middle of this molecule, if we bisect this, right down the middle right here, we get this mirror. Here's our mirror, right? That's your glass. And in the reflection in that mirror, you will see this dotted line, right? That's the reflection, but that's the other half of the molecule. So this has a mirror plane right here. And because of that, this molecule is achiral. Right? In fact, the mirror image of this, if we were to draw the mirror image is actually just the same thing. So that molecule here and this are identical, and therefore it is an achiral molecule. Now, as far as a little summary goes here, 2 things to kind of look at. Remember, an atom will be chiral, in other words, have a stereocenter, if it's tetrahedral and has exactly 4 different groups attached. Right? Different groups have different formulas or different connectivities, and we'll have some practice at figuring this out in just a minute. An atom with 2 identical groups will not be chiral. It'll be achiral. So the most common group that we're going to see for that is a CH2 group. So if we see that CH2 group because there's two H's there, then it must by default mean that that is not a chiral atom.